so nonlinear optimization tools in general seek some kind of sequence of combinations of parameter values, x0 as a starting guess that we gradually then refine, x1, x2, x3, that somehow converges to our parameter estimate where the gradient of the objective function is 0. So it seeks a combination of parameter values where the gradient of the objective function is 0, so that it's either maximized or minimized. And there are various strategies for doing that. One common one is gradient descent, where from a current position xi in the space of parameter values, we choose the next one of the sequence by taking a step in the most downhill direction that we can find from our current location. So that's one simple strategy. A slightly more sophisticated strategy is to use not only the local gradient, but also the local curvature of the objective function surface. So this matrix H is the second derivative of f, the objective function, expresses the curvature and can allow us to make a step more directly towards the minimum of the function. The plus side of these the methods that use these second derivatives is that they can get us to a minimum point more quickly. But a downside is that you have to compute this horrendous beast, the Hessian matrix. So, you know, often for a complex objective function, it can be difficult enough to derive and then encode the first derivatives of the objective function, let alone having to compute this whole matrix of second derivatives in order to implement things like a Newton's method. But there are good reasons for doing so. And so there are common problems with things with the basic gradient descent. It particularly runs into problems with particular shapes of objective function, which arise quite commonly. So things like long, shallow valleys tend to take gradient descent strategies a very long time to navigate. If you imagine, say, a kind of like a bathtub shape. So here's let me draw a kind of contour diagram of a bathtub. So let's say it's got very sort of steep sides. But then sort of, you know, has got a broad sort of basin at the bottom with a plug hole at the minimum point at the, you know, in the bottom there. So first of all, if we think about, you know, trying to locate that minimum point from a starting point on the rim of the bath, let's say we drop a marble on the rim of the bath and let it roll into the bathtub. If we drop it here, sort of directly to the left of the minimum point, the black spot, this will very obligingly sort of take and use a gradient descent strategy. It will very obligingly take perfectly downhill steps that take it directly to that minimum point. But if we drop a second marble, say over here somewhere, what would happen? Anyone tell me? What sort of behavior would that marble, which just always, you know, will go as downhill as it possibly can, what sort of trajectory will that marble take? It'll start by moving as downhill as it can possibly go, won't it, in that sort of direction? Keep going. Keep going. Keep going. What happens when it gets there? It sort of meets the bottom of the valley of the bathtub. Anyone going to give me an answer? I'm sure you know. Curve towards the right. That's sort of what we want it to do. And actually, you're right. Eventually, it will do that. So the answer someone wrote was it will curve towards the right. So actually what happens is because we're making sort of steps, finite steps every time, it will tend to overshoot. And then of course, the downhill position after it's overshot is back this way. And what very often happens with these gradient descent techniques is that they end up sort of oscillating around that sort of the basin of the valley. And it can take a very, very long time for it to it only moves, you know, the slope is very shallow towards the minimum point, and it only very slowly sort of finds its way along that valley. Whereas if you take into account the curvature, that can pick up on the shallow slope that's going left to right in this picture and take us in a sort of more direct trajectory towards this minimum point. So that's the sort of general motivation for using these second order methods rather than the very simple gradient descent. Okay, question from Sam. In this example, wouldn't it be traveling directly to the right, as that is in the direction perpendicular to the contours? So the red one, I think, would just travel directly to the right. But actually, if you, let's see, there, what's my color? So the problem here is, yeah, you know, maybe this isn't the best example, but once you get down to the bottom, you know, imagine that the sort of sides of the valley are a bit steeper than maybe I've drawn them here. You know, you can have something that sort of shoots up, back up the far side of the valley, then shoots back down again, and sort of, you know, yeah, I know what you mean. I've sort of drawn it a little bit too flat, probably at the bottom. The problem occurs when it shoots up the side of the valley, and so that, you know, the strongest downhill is across the valley rather than along it. That's when the gradient descent runs into problems. Okay. Yeah, all sorts of variations on these algorithms, and many of them accessible through the various functions in MATLAB and other mathematical programming environments. So in MATLAB, there's a function called fmin_unc. It stands for you know, minimizing f. The UNC is unconstrained, and we'll come back to constrained optimization in a second. So there's a variety of sort of modern techniques that actually sort of avoid some of the difficulties with these second order methods of having to derive and encode the second derivative matrix. Most methods these days will actually just compute it numerically from successive iterations of this algorithm. You know, as you look at consecutive points, you can make an estimate of the derivatives and the second derivatives, and that's what quasi-Newton methods do. You can also, if you're looking specifically at a least squares problem, you can approximate it from the first derivatives. That's the Gauss-Newton method. And then there are other sort of slightly more ad hoc techniques like Levenberg-Marquardt. The idea is to interpolate between gradient descent and Gauss-Newton, depending on what how the optimization is behaving at any particular point. Sometimes it's quicker just to do gradient descent, you know, if your objective function is decreasing rapidly. But at other times, if you detect that you've got stuck in one of these kind of oscillations, then only then do you bother to estimate the second order. And then there's a range of other sort of strategies, things like simplex and Powell's method don't require derivatives at all. And so those things can be very useful if you have, you know, a more sort of jagged objective function that isn't smooth, might have discontinuities in it. You can still use these methods to find the minimum point in some quite wild kinds of objective function. And also they're simpler to use because you don't have to figure out the derivatives and code them. So I mentioned constrained optimization. So constrained optimization is when you want to kind of avoid certain combinations of parameters because, you know, for various reasons, it might be that they're just not physically plausible combinations. You know, one of the parameters you're trying to estimate is only positive, for example. And so you want to avoid certain combinations and only conduct your search within certain regions of the full parameter space. Just to try and illustrate that, let's go back again to our simple child's height example. Let me draw our 4 points again. There they are. And let's think about that, the nonlinear model that we used, the last one that we looked at, this one. Actually, I'm just going to move it down a bit, need some space for this example. Down here. So we use that nonlinear model of our child's heights. I think there are sort of, actually, I'll draw this slightly differently just to make the example a bit more plausible. Put the axis a bit further away. You can sort of imagine two possible exponential curves that, that this equation expresses that might fit these four heights. There's one that might look like, something like this. An exponential curve that's sort of tending to some asymptote up here. And then another one, which might look more like that, which sort of tends to an asymptote in the negative direction instead. And let's suppose, my bad drawing aside, let's suppose that each of those two solutions fits those data points in terms of error score equally well. Is either of them preferable over the other, do you think? Is there something about one of those solutions that says this just cannot be a reasonable model of how someone's height varies as a function of their age? Anyone opinions on that? So neither of them is brilliant, to be honest, but this is a slightly contrived example. But let's think about this solution here. We'll call it X1. The problem with that is down here, isn't it? It goes negative. You can't have a negative height. It doesn't make any sense. So, I think one might argue that this solution is just not plausible. We look at the other one, X2. It's not brilliant either, to be honest, because it sort of shoots off to infinity as the child gets, heads into old age. But nevertheless, at least it doesn't do anything completely crazy, like say, the height can be less than 0. So I would suggest that maybe in this case, we would want to reject solution X1 and just constrain our optimization to find a solution of the type X2. How might we do that? Well, let's just think about what characterizes these different solutions. If we start with X1, so what do the values of our parameters look like for X1? Well, I think we can immediately see, because this is, as A, this is our age axis here, as A increases, the value of H according to the model tends to some kind of asymptote up here. And so I think we can immediately infer that M must be less than 0. M must be negative, because if it were positive, it would, this exponential term would explode to infinity as A tends to infinity, and it doesn't do that. It goes to an asymptote. So I think M must be less than 0. As A does tend to infinity, then with M being negative, so MA becomes minus infinity, I think, so then E to the minus infinity is 0. So that tells us that this asymptote here must be C. C defines this asymptote where the curve tends to, as A tends to infinity. So I think we can also write that C is greater than 0. It tends to a positive asymptote, so C must be greater than 0. Then finally A, so when little a is 0 here at this axis, this exponential has value 1. And so h must have value a plus c. And so that means the intercept here, where this curve hits the a equals 0 axis, must have value, the intercept has value a plus c. And I think that tells us that big A here must be negative, because that intercept a plus c is less than c, which is up here. Okay, so I think we can finally infer that A must be less than 0. Okay, so those are sort of constraints that characterize the solution that we don't want. Let's think about the solution that we do want, this x2. So here I think now, you know, the h does tend to infinity as a tends to infinity, so I think we can infer that m is greater than 0. The asymptote here, c, is sort of, it looks like it's just about positive, so I think we'll also write that c is greater than 0. And the intercept is now higher than our asymptote because it continues to decrease as we go into the negative end of the a-axis. So I think we can also infer that a must be greater than 0 because our intercept is at a plus c. So it looks like these are the constraints that characterize the solution that we're looking for in this particular problem. So we might then reapproach this problem and say, okay, only find us solutions that have positive values of m, c, and a. And that's what constrained optimization will do for us. And these are 3 different methods of imposing those constraints during some kind of optimization process. So let's start with the first one then, the transformation method. Very simple idea. All we do is replace the parameters of the model, which in general, an optimization algorithm will allow to vary over the full extent of the real line, can vary from -infinity to +infinity. We replace them with some function that transforms the real line into some smaller set of values that we're interested in. So, for example, to impose these constraints that each of our parameters is positive, we might write instead that h is equal to, let's call it parameter 1 squared x parameter 2 squared a plus parameter 3 squared. Then we can optimize the values of P1, P2, and P3. They can take any value along the real line, which our optimization algorithms will search. But then once it's converged and we've got values for P1, P2, and P3, we then transform them back into A, M, and C by squaring them, and that guarantees that the values of A, M, and C are positive, and guarantees that we get this particular solution that we're looking for. Okay, so that's very simple transformation method, and you can think of other transformations that can impose other kinds of constraints. Then soft or penalized constraints, also very simple idea. We simply add a big number to the objective function whenever the constraint that we're trying to impose gets violated. So, for example, let's suppose that we are using our favorite objective function, the sum of square differences. And let's suppose we want to impose the constraint that that's a poor choice of letter, isn't it? Overloading A here, let's say M. We want to impose the constraint that M is greater than 0. So the sort of thing we might do is just add some massive number, 10 to the 20, let's say, every time, whenever the value M is less than or equal to 0. So we can write that mathematically. There's a thing called the Heaviside function, which is equal to 1 if M is greater than 0, 0 if M less than or equal to 0. So we might then just add to our objective function enormous number plus, actually, so it would be heavy side of minus m here, wouldn't it? Because we don't want to add the big number when m is positive. We only want to add it when m is negative. So that's a very simple penalized constraint. A bit of a brutal solution because, you know, the objective function tends to, you know, if we were to plot it as a function of m, let's say 0 is here. So the, you know, objective function would be nice and might be nice and smooth all the way down to 0 and suddenly fires up to 10 to the 20, you know, has a massive discontinuity at 0, which can be a little bit difficult to handle for an objective function. So the idea of a soft penalized constraint is that you at least retain some kind of continuity at 0 by perhaps adding a linear term here rather than plus 10 to the 20 heaviside function. You would also multiply it by the absolute value of m, say, and then you get a sort of linearly increasing penalty as you move further into the forbidden zone of m being less than 0. Okay, so that's soft and penalized constraints. Again, very simple idea. And then there's some more sophisticated ways of imposing constraints that allow you to impose some more sophisticated constraints. So, for example, if you you know, you might want to impose a constraint, say m plus c plus a equals 0, some kind of linear constraint on the parameters, or, you know, a linear inequality, something like that. The sum of the parameters is less than 0, or even some complicated function of those parameters, you know, something random like that. You can imagine much more complex constraints that you might want to impose in certain conditions, and using more sophisticated techniques like Lagrange multipliers and active set methods, you can do this kind of more complex constraint. And there's another function in MATLAB called fmin_con, as opposed to fmin_unc, was unconstrained, con is constrained, that implements these various methods, or actually implements specifically these methods in the last bullet point, and allows you to impose some various, some quite complex constraints should you need them. But for simple constraints, you know, actually these methods up here are often actually a little bit more effective and efficient than some of these more exotic ones. The transformation method in particular is pretty effective if you just want to do something simple like constrain a parameter to be greater than 0. Okay, let me pause. Any questions or anything at this point? All happy? Okay, I shall continue. So perennial problem with nonlinear optimization is the issue of global and local minima. So unless you've got a very simple and friendly objective function, you pretty much always run into this problem with nonlinear optimization, which is that if there's more than one minimum in the objective function surface, then the solution that it finds will depend on its starting point. So here, for example, if we were to start a gradient descent search from somewhere on the right-hand side of this function, up here, say, it would happily move downhill until it finds the global minimum. But unfortunately, if we were to start it from a different random location over on the left here, we would move happily downhill. But once we got to the bottom of this local minimum, we'd find a point with 0 gradient and stop there. And the problem is that whenever we find a minimum point, we're never sure if it's the true global minimum or best solution that minimizes the overall objective function. And this, you know, this example that I'm showing on this slide, this is a simple one. You know, actually, when we start looking at real objective function surfaces for real modeling problems, they're much more complex surfaces than that, and tend to, you know, might look more like this picture here, this is a contour map of the a small area in somewhere in the Lake District, I think. And you can see, this hilly landscape produces lots of different local maxima all over the place. And there's only one global maximum in this area. I'm not sure which one it is, actually. It's either this Cady Hill over here or possibly Tabor Hill over here. And we can see that because we've got this nice global view of the whole surface, but that's not what a typical non-linear search will have. It won't be able to see this full picture. It's more like a sort of blind hiker who starts somewhere in this, say they start somewhere in this village of Stow and wants to find the highest point in this local area. How would they go about doing it? So what they might do is come out of their hotel, sort of put their foot in a circle around them and identify the direction that's most uphill from there, like our gradient descent algorithm, take a step and repeat the process until they reach a point where every step takes them downhill. Is that likely to find the highest point on this map? Highly unlikely. More likely that they might end up in, one of these small maxima that's sort of local to the position that they started in, maybe this one or one of these ones or this one or something. But actually quite unlikely that they would find a path that takes them up to the top of this global maximum in the local area. How might we devise a strategy for our blind hiker to find the true global maximum of this little area of landscape? Any ideas how they might increase their chances? No ideas? Yeah, that's a good idea. So many initial points. What you might do is do a sort of strategic search where you identify lots of different starting points, perform that same procedure and keep track of which one of those starting points has led you to the highest point. Run that lots and lots of times, and hopefully at least one of those starting points will take you on a path that leads you to the global maximum. And that is, in fact, a very common strategy for trying to find global maximum with techniques like gradient descent. You might start from a grid of starting points over a sort of predefined subset of the area. You might just use random starting points, some advantages to that in some cases. But the problem is that you never really know if you've managed to identify the true global maximum with a strategy like that. You can certainly increase your chances, but you never really know if you found it. Other popular techniques out there's an idea called simulated annealing, which uses more random sampling, allows you to take uphill steps with some certain probability, and gradually over a period of time uses an annealing strategy which reduces the size of steps in such a way that you can actually guarantee under certain conditions that eventually you will converge to the global maximum of an objective function. However, it might take a practically infinite amount of time for you to get there. So in practice, it's not quite so effective. Then there's a bunch of population. Decline, someone's calling me. Population methods, which things like genetic searches and migratory algorithms, where you maintain a population of candidate solutions that can share information between themselves, might originally be randomly scattered over the landscape of possible solutions, but they can alert each other to areas that show promise as being the global maximum, and gradually over generations and generations all converge on a global maximum of even quite complex objective functions. And these sorts of techniques can prove extremely effective for very challenging objective functions, with crazy discontinuities and maxima and minima all over the place. Can actually be more effective than things like gradient descent, although they often have a bit less accuracy because gradient descent will actively seek out the minimum point, whereas these just seek out areas where generally the values are low. Okay, I think is that the end of that section? I think it is. Yes, slide 19 and 19. Okay, so that's all I'm going to say, about the sort of basic principles of parameter estimation. In the next section, we're going to move on to, a specific application, which hopefully will make all this a little bit more concrete.